is Sarah Barker. I want to first and foremost thank you for joining us for our monthly Celigo user training webinar. Today, as I'm sure you're familiar, we're joined by Sarah Kessel. She'll be our presenter today. She is our application scientist and lab manager in our San Diego location. Sarah's been with the Celigo since its inception and is a wealth of wonderful knowledge. And today she's presented us, put together some content on how, or getting to know the Analyze tab parameters on the Celigo. And I want to thank our audience because this is actually a recommendation for a topic to be presented that came from past attendees, is how do all of these things work. So this is going to be, I think, a great presentation. I'm actually looking really forward to this content as well. As we do with all of our webinars, everybody is going to remain muted throughout the duration of the presentations. If you have any questions or comments as we go along, you can type them into the questions bar there on your dashboard on the right-hand side of your screen. We will have time after Sarah's presented her content today to answer any questions on anything that we cover or anything that maybe we don't cover and you just have questions on. This webinar is for you, our customers. Additionally, as always, we will record this, and if you want to watch this again or send it to somebody else who might benefit from the content after we've concluded today, I will be sending out an email with the link to the recording, so you'll have that as well. Without any other further ado, I'm going to go ahead and pass this over to Sarah, and we can get started today.
Thank you, Sarah. Hi, everyone. Thanks for attending today. As Sarah mentioned, that this content that we're presenting today has been requested a lot. So when you're new to imaging, you basically are going to be experiencing some new words, some new science. So this is basically going to help you understand image analysis in the realm of image content analysis. So let's get started. So in this image here we have the workflow of the Celigo software, and we're going to focus all of the content today on the Analyze tab. It is not going to be application specific, but more about button behavior. So here's an example screenshot of the Analyze tab parameters. So I break it down into three sections. The general section, which is up there at the top, and then I work my way down into the identification section, which helps me identify what are the objects in the image. And then after that, all those settings are set. Then I work into the pre-filtering section, which is at the very bottom. So as you can see, it's numbered 1, 2, 3, and so that is my workflow. I work from the top and then work my way down to the bottom. So let's start off with the first section, which is the general section, and it's basically focusing on the well mask. I want to show you some different images of different well types to showcase how the well mask functions and helps. So here we have an example of a 24 well plate. So most large well plate types have clear walls and are not manufactured for imaging, so they're not exactly perfect. So here we have adherent colonies growing on a 24 well plate, and the goal is to count those colonies. And so if you turn on the graphic overlay, for this application we're using single colony verification, you can see that we have detected the objects in the well, but we also have picked up objects outside the well wall. And that's because there is no limit to the image analysis when you take the picture out to the edge of the well. So what we need to do is turn on the well mask, which is basically localizing the image analysis to be inside the well wall and excluding the outer areas past the well wall. So when you turn on the checkbox, an orange line appears on the image. And currently we have the well mask usage mode set to original. So what is original? It is the dimensions coming from the manufacturer's plate specifications. So you can see the orange line coming from the plate manufacturer isn't exactly perfect with this plate. But if we use the automatic, which is using those dimensions, plus it actually is incorporating an algorithm to better define what is the well edge. You can see how it sits now right on top of that well wall. Now it's a little bit outside the area. It's picking up still some objects on that well wall. So what we can do additionally is shrink the well mass. So currently it's set at 100%. So if we just move it down to 99%, then you can see how the orange line will just move inside the well area. And now we've eliminated those objects from being detected, and we're really focusing the analysis to be on those colonies inside the well. So for these large well formats, I recommend using automatic and maybe shrinking the well mass to 99%. Now, this is just one well type. I next want to move into another kind of well plate format. This is a 384 well plate that has, it's a square well with rounded edges. And this can be challenging to try and draw an accurate well mask. In this example image, we have some Drax 7 staining of dead cells. So it's a far red dye, and you can see the dead cells there. And then you can also see there's a little bit of background in this image. So the stain has a little bit of background, which towards the edge of the well, it can actually incorrectly pick up objects at that merged point where you have the well wall and the background image. So those objects are being picked up in the center just fine, but on the edge we're picking up incorrectly the well edge as objects. So this is another case scenario where you want to use the well mask. So let's turn on the well mask by just checking the box. And here we have the automatic mode turned on. And this merges a square with a circle to create rounded corners. So this is how we've overcome this unusual well shape. It's not exactly a square. It has those rounded corners, so this is how we accommodate for that. Now the original, which is the plate manufacturer specifications, is a square, and that's what this looks like. So you can see how that doesn't function very well for eliminating those objects, but the automatic does a better job. We're still picking up some objects here at the bottom that are just outside. So let's shrink the well mask until we can eliminate those extraneous objects. So I just keep shrinking the well mask till it eliminates those objects. And I've found for this plate type, around 95% seems to work pretty robustly for the whole plate. So for this well type, I would actually recommend using a 95% well mask for this. Now, if we actually navigate to another well that has drug treatment with a lot more objects in it, you can see how still that you're going to pick up the majority of your cells with no problem, and only a small amount, let's take it, there we go, and then there's only a small amount of objects that are outside the well mask that are not being picked up. But if your plate is globally analyzed like this, every well will be treated the same, it'll be just fine. So it's doing a really good job now, picking up only the objects that are counted as dead cells. Now let's look at a control well just to showcase the difference. All right, so it's working really well. So again, for this plate type, 384 black wall, square with rounded corners, I recommend automatic with 95%. Here in this example is a 96 well black wall plate. This is probably one of the more common plates that is used on the Celigo. So it also can struggle with imperfect well shapes. So even though the manufacturer gives specifications, the plates are not always that perfect. So again, we're using the automatic well mask for usage mode. And you can see that it's just a little bit outside the well wall where we're picking up objects. And we don't want those objects. So let's switch it over to original and see what the manufacturer specifications say it should be. So here it is inside the well wall, so that's a little too further out. Let's move back to the automatic. And let's just shrink it down from 100% to 99 and see if that improves. Yep, 99% is much better. So this is what I would recommend for a 96 black well plate. Now let's go back to the large well plate types. These applications like Colony and Confluence have unique viewing and analysis features. In the well map on the lower right, you can see that we have displayed FOV, which is field of view, which is showing one camera per image per display on the screen, or field of regard, which is actually 16 images that will be displayed on the screen. That's what we're currently looking at. Or you have the option to look at the whole well. So these features allow you to actually put in the image display area more than just one image. For large applications, this is hugely beneficial. So we're currently looking at the single colony verification applications where we want to count colonies. The other feature that is unique to these large applications is analysis resolution. Because we're not looking at single cells but large colonies, we don't need to have that fine resolution of 1 micron per pixel analysis. We're actually taking a 1 micron picture, but we'll actually analyze it with less resolution. So for these applications, the default is set at 2, but I want to show you how the analysis resolution, as you increase that value, how it affects the graphic overlay, and what I would recommend for these kind of applications. So let's zoom in so you can actually see the cells. So it's doing a pretty good job with 2 microns, so you can see where 1 micron was not going to get you any better. If anything, also, the higher the value, the faster the analysis too. So 1 micron would just take forever for these large well types, but as you increase that value, it becomes much, much faster. And let's take a look at this particular colony and adjust the resolution to be higher, or at least increase the value so the resolution is lower. So let's move it to 3. The image will recenter and scale itself. Now I'm moving up to 4 micron, 5 micron, and 6 microns. So the object hasn't changed too much, but when we get back up to higher values than 6, you can see the outline changes a little bit. So for these type of applications, I would recommend between 3 and 6 micron per pixel. This will also decrease your analysis time overall. So again, those are analysis and viewing features for large applications. So we've covered the general well mask area. Now I want to move into the object identification and pre-filtering. So here's some background. The camera image pixels have values where 0 is black and 255 is white. The algorithms decipher what is an object according to pixel intensity threshold settings that separate the background from the objects. For example, the bright field algorithm looks for objects with a bright center and dark edge. So if you think about your adherent cells, they have a background that's gray, and then you have the dark edge and the white center. If we drew a line over this cell and actually mapped out the pixels in that line on a value based on its pixel intensity, it would look something like this. You can see you have the background at around 125, the dark line from the outside, and then the bright peak at the center. Then if you use an intensity threshold value that actually separates the background from that peak, that red line is your intensity value to type in on the screen or on the software. Then the green outline that you see is displayed is from the pixel intensity above that threshold. So that's how the cells are actually being detected and counted. So for the fluorescent algorithm, let's look at it looks at the fluorescent objects with the bright pixels over a dark background. So for instance, you have your GFP transfected cells, Hooke staining for the nuclei, you have the PI dead stain cells. This is going to have a black background with a very bright signature, almost to saturation. So here, if you draw a line over your cell and plot those pixel intensities, it will look something like this. Then you use your intensity threshold value to draw what you would be able to draw a graphic outline around any pixels that are above that threshold. So the other algorithm I rarely ever use is the dark object algorithm. It's looking for dark objects with no bright center. It's included in the software, but I rarely ever use it because it can struggle with a lot of objects that are not cells but more debris oriented. But this is what the pixel intensity values would look like if you were to graph them. And then there's the last one is the texture algorithm. The texture algorithm looks for texture differences between the objects found and the background areas. This is recommended for large areas or large objects such as colonies, spheres, confluence measurements. Here we have an example of a colony grown on a plate, and you can see that there's a lot of texture in it. So if you drew a line over this object, you can plot those pixels and then draw an intensity threshold. You'll see anything above that threshold value is where the graphic overlay will be drawing its line, and that's how a colony or confluence measurements are drawn. So let's show how the bright field algorithm and intensity threshold work together to help identify your adherent cells. So here we're using the bright field algorithm, and the intensity threshold defaultly comes up at 15. So this is currently picking up only the really bright cells that you see in the image display here. So the adherent cells that are really close to the background are missed with this high value. So what you'll need to do is lower the intensity threshold value. Let's step down in groups of 5. So let's go from 15 to 10 and see how the green graphic overlay will expand, and it'll also pick up additional adherent cells. Let's go further down. Let's see what 5 looks like. It's doing a better job. I like 5. But just for kicks, let's go through and see what lower values would actually showcase. What lower values would do for adherent cells or confluent areas, it tends to merge objects together and pick up smaller debris, which is not a cell. So let's even go down to 1. That's the lowest value we can put in. Now we're picking up way too much in the background. That's not what you want. All right, so let's go back to 5. I kind of like that value. It looked good for that whole colony. Okay. Now that's doing a pretty good job. I would probably stick with that, but I also want to showcase to you the next grouping down is the cell diameter. I want to focus on how that portion of this identification section can influence the graphic overlay. So these flat cells that have kind of been detected as 2, currently we can use this cell diameter parameter to help better fit those types of cells. So it's actually asking what is your average expected size of your cells. So we know that this is a 1 micron per pixel image. So just by increasing the cell diameter here to something more of this population, which is probably between 10 and 15 microns, you'll see that the objects that were flat and detected as 2 are now merged as 1 and better identified. Now the next button down is the background correction. I turn this on for bright field images. It helps when you have dark edges on the well. So right now this image is not having too bad of a dark edge, and turning it on and off right now doesn't show too much of a difference. But when you have plates that have been growing over time, the evaporation of those wells will lower the liquid, and you can see a dark meniscus show up on your edges. And this is where background correction will help pick up cells that are in those dark areas. The next button down is the separate touching objects. I used those, basically this separates objects that are close together that are currently identified as 1 but need to be separated into 2 or more. So adherent cells that are close to each other, you can see here we've got 1 cell or 2 cells, maybe 3 merged in 1. By turning on separate touching objects, it breaks it up into multiple cells. So right now we've got about 3 in that little cluster area. So between separate touching objects and cell diameter, it really depends on your cell type. If you have really long cells, I would probably not use separate touching objects because it will chop them up. If you have suspension cells, I would turn on separate touching objects. Confluent cells that are all close together can benefit from separate touching objects. Now that we've identified the cells in the image, we have a few extra items that I want to remove. So that is the lower section down here called pre-filtering. The first parameter you can remove items is using the cell area. So here we have it set at 10. If we move it up to 20, we can start to remove these teeny tiny little objects. And let's go up again into a bigger value. Let's try 30 and see if we can remove some of these little extra pieces. Yep, that's doing a good job. And we can continue to move up in values just to see how it behaves. So this is allowing you to be able to remove items that were picked up from the identification section that are bigger or that are smaller than your minimum requirement size. But you also have the upper range that you can eliminate if you have large, crazy debris that you want to eliminate. So 60 seems a little bit too much. I'm starting to lose some of those clusters in the center of this, or some of the cells in the center of this cluster. Those bright cells that are all growing on top of each other. So maybe let's move back down to 40. That seemed to be a good fit for this cluster of cells. All right, that looks much better. Now, once you like your settings, at the top you can save your analysis settings for later recall. You could call this adherent cell type A or whatever, and then use it for another day's analysis. The next section down is cell intensity range. It allows you to filter out objects according to their pixel intensity. This doesn't have a whole lot of objects that are that I would want to filter out by intensity, but you can see how it works. If I were to say if I wanted to remove those really bright cells, basically how you would see the pixel intensity displayed down there, you hover your mouse over the object you want to eliminate, understand what its pixel intensity value is, and then you would adjust the slider to remove the objects in that range that you don't want. So just for kicks, let's remove this really bright cells that we originally picked up just by decreasing the high end, the white cells from the image for the graphic overlay. So now we're approaching the background, 150, 128. There you go. You can see that we've removed those really bright cells using their pixel intensity. So this is just to show you how you can eliminate objects using pixel intensity. I rarely use this for bright field cell counting. I might use it if I have a fluorescent image where I have some really bright, crazy, erroneous debris in there, but that's rare. Now the last button on the bottom is called minimum cell aspect ratio. If you think about a circle, the height and the width are equal to each other, so the value is 1. So this is allowing you to eliminate objects that are less than perfectly round. So you have adherent cells that are really long. You can identify the really round cells are close to 1. Adherent cells will be less than 1. So let's just for display to show you, let's move it up in value. So let's put in 0.1. Nothing quite removed here. Let's move it up to 0.2. And now you can see really long objects or irregularly shaped objects were removed from the graphic overlay. We want those adherent cells, so let's move it back down. Okay. So you can see how this aspect ratio will help you remove irregularly shaped objects if you have some debris that's crazy, in shape, it will help maybe to set it at 0.1. That way your adherent cells that are long are still accepted, but your crazy debris is removed. Now, going to severe values like 0.3 showcases how you could actually use this tool to identify objects like rounded up cells. When you're looking at cytotoxicity where drugs have been applied to adherent cells, those cells will round up after drug treatment, and you can now isolate and count those rounded up cells. So that's one of the features that you can probably use if you're looking at cytotoxicity. Now, we've been looking at adherent cells. This is how I would recommend either using the bright field or fluorescent algorithm to look at suspension cells. So here you have your bright, bright, bright center of the cell in dark ring. Currently, the default settings for this application is set from bright field with 4 and 10. Now, the graphic overlay, as you can tell, is picking up way more than the cells. It's got stuff between the cells that are being picked up. That's because the intensity threshold is really low. Remember, we were looking at 5 for adherent cells to pick those cells up. For these rounded up suspension cells, we can go much higher. So let's go up in groups of 5. So here you can see we're eliminating some stuff. Let's go to 15. And then we can go to 20. It's doing a better job removing some objects that are not cells. Okay, 25 is looking really good. I like that. So it's picking up a good amount of the cells and eliminating anything extra. Let's see what 30 does. Now, if you'll note that the dead cells, those little cells that are not being picked up, are not counted, just to note. Now let's see how the cell diameter is affected when you change that to pick up the cells. So the default was set to 10. Let's see what 6 looks like. And let's move the intensity threshold up now to see how it behaves with the 6 diameter. 15, it's looking good. It's kind of looking the same as before. So moving that cell diameter from 10 to 6, it improved it a little bit, but for the most part, I think the intensity threshold is the setting that was more critical in proper identification of these suspension cells. So setting it up to just the diameter wasn't helping too much, but the focus was better on the intensity threshold. Now, we've been looking at this as a bright field algorithm, but because of the super bright centers of these suspension cells, I'd like to show you a different way of analyzing this image using the fluorescent algorithm. So let's switch this back to the default settings. From 25, let's switch it back to 4 and 10 for diameter. And switch the algorithm from bright field to fluorescence. Now you can see that the outline is focusing on the bright center of those suspension cells. And let's move the intensity threshold from, it's a little bit of shadows to the edge of the wells, or edge of the cells. So let's increase the intensity threshold from 4 to 10 and see how it behaves. Remember, the fluorescent algorithm is looking for a black background and then a bright peak. So the dark ring of the cells is kind of behaving like that dark background. So it's identifying the cells that are in suspension, that bright center, much easier. And it looks very similar to what we just saw a second ago with the bright field algorithm set to 25 intensity threshold. So it's doing a really good job. So this showcases how you can do either one. So if you're struggling with the bright field algorithm, note for suspension cells, you can also switch over to fluorescent algorithm to pick up those cells. And again, here is the bright field algorithm set to 25. It looks very similar to that fluorescent algorithm. So that just shows you some flexibility in suspension cells. Now let's move over to an actual fluorescent image using the fluorescent algorithm. Here we have a blue stained Hooke's nuclei, or a Hooke stained nuclei. Now the image is actually black and white when the camera takes it, but the software actually pseudo-colors it for display on Celigo. So let's artificially change it back to a white, black and white picture. This is a little bit easier for me to explain what we're going to show on the analysis. So the default settings are set for fluorescence 4 and 10. And when you turn the graphic overlay on, you can see how the nuclei are being picked up pretty good with this fluorescent stain. So generally when I've done the Hooke staining, I stick with the default settings, but they're pretty close. Now you have a few cells that are really dim. To how you can pick those cells up, you can actually measure the size of the cell with hovering your mouse over an object and seeing what the cell diameter is. So currently you're at 817, move it over to the right and you get 830. So that's about 13 microns. So you can say that the nuclei have a size between 10 and 15. So currently you're at 10. Let's bump it up a little bit to say 12. And see how the graphic overlay increases and those dim cells are now being picked up as a whole. Let's move it up to 15. So it's increasing the graphic overlay for the objects that we found and also picking up some very dim nuclei. But you'll notice also that the nuclei that are really close to each other are also being merged as one. So now at this point we can use that Separate Touching Objects button to help separate those nuclei into two. Okay, it's doing a better job now. So those are the few parameters that I might change if I'm having some really dim flat nuclei and they're close together. That looks pretty good. Now in the upper right area you can see that there's a couple small, or one small object that I want to remove. It's so few in this image, but just to showcase a pre-filtering, you can see that if I move it up from 10 to 20, okay, 20 didn't remove it. Let's move it up to 30. There you go. So now you can see how pre-filtering removes objects that are currently detected. If you're going to be using the gating tab, I just want to point out you can also filter out objects in that tab versus doing it in this area. So and that's actually what I would recommend doing. So if you're going to do some gating, which next month we'll cover gating tab, I can show you that portion. Okay. So here we're back to that 96 well with the black wall and the colonies. Now I want to show you the other algorithm, which is texture. This texture algorithm works well for Confluence and the Colony suite of applications. And the default values do a pretty good job for your starting point. So you'll note that the intensity threshold is set at 15 and the precision is set to low. I usually keep it at low because you really don't need a whole lot of detail when you're looking at colonies. You do when you're looking at individual cells, but for the colony applications or Confluence, low precision is actually better. And it's actually much faster in the analysis. You can see when you switch it to high, you get a lot more extra detail around the colony, but it doesn't change the shape or the size too significantly. So having this precision set to high is only going to slow down the analysis, and it's not going to add any more information that you need in the end. So I would recommend using the low precision for these large texture type applications. And normal didn't do anything, so here's the low. It looks pretty good. And you're basically looking for counts and size of the colonies. So now we've basically covered the general section, which is covering the well mask, and for some unique properties of the larger applications like colony and confluence, such as the analysis resolution. And we also covered how to identify an object, particularly using those different algorithms, and then how to eliminate objects that are being detected that you don't want to be called as a cell. Now that's a lot to cover in a day. There are more things that I could talk about. I'd like to save those for another session. Maybe have another analysis setting webinar on larger applications like the confluence and colony applications. So at this point, I've given you a lot of information, and I'd like to open up the forum for questions.
Thanks, Sarah. That was a fantastic presentation. So as Sarah mentioned, we do have time for questions now. So if you have any questions on anything that was presented, or even if you just have a question on something completely different, we are here for you, and we would like to answer anything you might have on your mind. Go ahead and type your questions into the questions bar, and we can certainly go through those. I'm not seeing any questions coming through, which could be a good thing.
I don't know. It's a lot of information.
I think the one thing that surprised me that I learned today was you can use a fluorescent algorithm if you're looking at a bright field image. I think that that was not intuitive for me, so I thought that that was really helpful.
Which I also, the reason I showed the slide in the beginning about how those algorithms work really, to me, give you a mind's eye of what's going on in those images. So the fluorescence does work for those suspension cells.
Absolutely, because just the way the software is looking to detect what it's going to identify as a cell. Exactly. Yep. Fantastic. I'm still not seeing any questions come through. So if you're if you're watching this as a recording, you can certainly reach out to us at support@nexalum.com, or you can always give us a call, or reach out to your local application scientist. We have them, 15 of them throughout the United States, and also overseas internationally. I want to thank everybody for joining us today. We know that your time is precious, and we appreciate you taking your time to join our webinar. And certainly I want to thank Sarah Kessel for putting on another fantastic webinar, and I cannot wait for next month for the gating tab. The goal here is just to help you feel much more confident and comfortable using your Celigo. Next month's webinar will be August 11th, the second Thursday of every month. And I want to, again, thanks everybody for joining, and have a great day.